Hello and welcome to today's video on temperature stress, otherwise called thermal stress. So let's pick this question to analyze the effect of temperature stress on a compound bar. The question says, a short bar of copper 25 mm diameter is enclosed centrally within a steel bar of external diameter 30 mm and thickness 3 mm at 0 degrees Celsius. The ends of the bar and tube are rigidly fastened together and the complete assembly treated to 80 degrees Celsius. Calculate the stress in the bar and the tube if Young's modulus for copper is 100 by 10 to the power of 3 newtons per millimeter squared and Young's modulus for steel is 200 by 10 to the power of 3 newtons per millimeter squared. And the coefficient of linear expansivity in copper and steel are 0.00001 per degree Celsius and 0.000006 per degree Celsius respectively. So let's pick out our parameters. First, we are given a short bar of copper 25 mm diameter. So diameter of copper, okay, diameter of copper, let's use DC to represent that 25 mm. We convert this to meters. This becomes 25 by 10 to the power of minus 3 in meters. Okay, enclosed centrally within a steel bar of external diameter. So external diameter of steel bar, external diameter of steel. So we'll simply use small dx for external diameter. Okay, is simply 30 mm, which is 30 by 10 to the power of minus 3 in meters. And thickness of steel, let's use TS for that, and that's equal to 3 mm, which is actually 3 by 10 to the power of minus 3 in meters. So before proceeding, the essence of giving us external diameter, so we're going to be using capital D for the external diameter, please. So the essence of giving us external diameter for steel is just because steel actually has an internal diameter. Okay, so we're giving both external and thickness simply because the steel material has an internal diameter. So there's a need to find the internal diameter so that we can be able to calculate the area of the steel material. Now, to find the internal diameter, we make use of this relationship. External diameter D of steel is equal to the internal diameter plus 2 times the thickness. So this simply implies that the internal diameter of steel becomes the external diameter of steel minus the 2 times thickness. Okay, therefore the internal diameter of steel, which is small ds, is now equal to, so this is now equal to external diameter give us 30 mm, which is 30. Okay, you can simply use 30 minus, since thickness is also in millimeter, you can keep it like that. Then after solving, you can convert. So you have 2 times thickness is 3 mm. So this is actually 30 minus 2 times 3 is 6, and that gives us what, 24 mm. So this simply implies that the internal diameter of steel is 24 mm. Otherwise, 24 by 10 to the power of minus 3 in meter. So this is the internal diameter of steel. Alright, having found the internal diameter of steel, let's say continue picking out our parameters. We are given initial temperature 0 degrees Celsius. Initial temperature from the question. So T1 was given as 0 degrees Celsius. Final temperature T2 was given as 80 degrees Celsius. So with this, we can be able to now find the change in temperature. Therefore, change in temperature, which is delta T, is T2 minus T1, and that's simply 80 degrees Celsius minus 0 degrees Celsius. So this implies that change in temperature equals 80 degrees Celsius. Okay. Question says calculate the stress in the bar and in tube if the Young's modulus of copper. So we're given Young's modulus of copper. Let's use EC for Young's modulus of copper. It was given as 100 by 10 to the power of 3 newtons per millimeter squared. So we need to convert this to newton per meter squared. That is simply multiplying this equation by 10 to the power of 6. So you have 100 by 10 to the power of 3 multiplied by 10 to the power of 6. Okay, that becomes in newton per meter squared. So this means the Young's modulus of copper is actually 100 by 10 to the power of 9 newtons per meter squared. Okay, similarly, we are given Young's modulus of steel. So the Young's modulus of steel was given, so let's use ES for that. It was given as 200 by 10 to the power of 3 newtons per millimeter squared, which we also have to convert now, simply multiplying this relationship by 10 to the power of 6. So we have 200 by 10 to the power of 3 multiplies 10 to the power of 6 newtons per meter squared. So this simply implies that the Young's modulus of steel is 200 by 10 to the power of 9 newtons per meter squared. Okay, so those are the values of the Young's modulus. Aside that, we're also given the linear expansivity of both cases, both steel and copper. So let's flip over and continue writing down our parameters. So we're given linear expansivity, okay, of copper as alpha C was given as 0.00001 per degree Celsius, whereas that of steel, let's use alpha X for that, was given as 0.000006 per degree Celsius. So these are our parameters given to us. So having found out our parameters, let's now start our calculation. We are asked to find stress in the steel, unknown, and stress in the copper, also unknown. Now, when analyzing temperature stress, the first thing to consider is the strain of the materials. The strain of copper, okay, the strain of copper plus the strain of steel is simply equal to the change in thermal expansivity or linear expansivity. In this case now, the higher linear expansivity comes first minus the lower linear expansivity. So the higher linear expansivity on comparison is the linear expansivity of copper. So this simply means linear expansivity of copper minus lower linear expansivity, which is that of steel now. So minus linear expansivity of steel multiplied by the change in temperature. This is our first equation. Whenever you want to solve any problem in temperature stress, the sum of the strain is equal to the change in thermal expansivity multiplied by the change in temperature. Okay, but you recall that strain E is equal to the stress of a material all over the Young's modulus of that given material. So that simply means we can write this equation a little bit. This becomes in place of stress, in place of strain of copper, that means we are going to be having stress of copper over Young's modulus of copper plus in place of strain of steel, it becomes stress of steel over Young's modulus of steel, and that is equal to thermal expansivity of copper minus thermal expansivity of steel multiplied by change in temperature. So this is the first thing to do. So let's put in the parameters now. These are what we are looking for: stress of copper and stress of steel unknown, but we know they are Young's modulus. Let's put in their values. Okay, so the stress of copper all over the Young's modulus of copper was given in the question. Let's get it and see. Alright, so not forgetting, the Young's modulus of copper was given as 100 by 10 to the power of 9, whereas Young's modulus of steel was given as 200 by 10 to the power of 9. Okay, so from here now, the Young's modulus of copper was given as 100 by 10 to the power of 9 plus stress of steel all over. The Young's modulus of steel was given as 200 by 10 to the power of 9, and this is equal to the thermal expansivities Thermal expansivity of copper we know already was given as 0.00001 minus thermal expansivity of steel was given as 0.000006 times the change in temperature. We did that earlier and we had 80 degrees Celsius. So multiply by 80 degrees Celsius. Okay, so now we are going to be taking the inverse of these values. Okay, so this is simply saying 1 all over 100 by 10 to the power of 9, okay, times sigma c plus again 1 over 100, 1 over plus again over here we have 1 divides 200 by 10 to the power of 9 multiply sigma s. So we're simply taking the inverse of this value so we can have a linear term. So let's obtain 1 divides 100 by 10 to the power of 9. And that simply gives us this is now 1 by 10 to the power of minus 11 sigma c plus also let's obtain 1 divided by 200 by 10 to the power of 9. So that simply gives us 5 by 10 to the power of minus 11 sigma s. Okay, and this is equal to, now we obtain this multiple, this difference and this multiple. So 0.0001 minus 0.6 multiplied by 80. So this simply gives us 3.2. So this product here gives us 3.2 by 10 to the power of minus 4. Alright. So at this point, we can simply call this equation 1. Okay, we can simply call that equation 1. So the first equation is to write the strain equation. The sum of the both strains are equal to the change in their linear expansivities multiplied by the change in temperature. Now, the next thing to consider when solving any question involving thermal stress or temperature stress is the load carried by each of them. The push experienced by the material with lower thermal expansivity is equal to the pull exerted by the material with higher thermal expansivity. So that simply means that pull by copper, that's simply PC, is equal to push by steel, that's simply PS. Now, this pull and this push are simply what? Force. So this is simply telling us that the load or the force on copper is equal to the force on steel. That's what the equation is simply saying. All right. So if this is so, recall that load is actually stress times area, not forgetting load simply means stress times area. So this actually means that the pull by copper or the force of copper is simply stress of copper times area of copper, and this is also equal to the push on the steel. This simply means the stress of steel multiplied by area of steel. So from here we can make the stress of any of them subject. Let's say we are making stress of copper subject. This simply implies that stress of copper is equal to the stress of steel multiplies area of steel all over the area of copper itself. So this is how to find the stress of copper. So all we need to do now is find the area of steel, find the area of copper, then impute it into this equation and obtain a relationship for stress of copper. Okay, so let's get their areas now. Area of copper, AC remains pi over 4 diameter of copper all squared, and this is equal to, what is pi? Pi is 3.142 multiply diameter of copper was given in the question. Let's flip over. So diameter of copper was given in the equation simply as 25 millimeter, which is 25 by 10 to the power of minus 3. Okay. So diameter of copper is 25 by 10 to the power of minus 3. Remember, all squared all over 4. So this helps us to find the value of the area of copper. So let's obtain the area of copper. So the area of copper gives us 4.9 by 10 to the power of minus 7 a meter square. This is the area of copper. Is minus 4. Okay. 4.9 by 10 to the power of minus 4, not minus 7, please. 4.9 by 10 to the power of minus 4 in meter squared. So that's the area of copper. Next, we'll find the area of steel. But observe that steel is actually a hollow material. So it has external and internal diameter as was given in the question. So we've obtained the internal diameter and we know the external diameter. The area of steel itself, okay, area of steel, since it has both external and internal diameter, please let's highlight this for area of copper. Okay, so area of steel is simply pi all over 4 the external diameter of steel squared minus the internal diameter of steel all squared, and this is equal to pi over pi remains 3.142 divided by 4 into the external diameter was given as 30 millimeter, which is 30 by 10 to the power of minus 3 all squared. Okay, I think we can pull this down. Okay, minus the internal diameter of copper actually, the internal diameter of steel actually gives us 24 millimeter, which is 24 by 10 to the power of minus 3. Okay, let's take it down a little bit. So the area of steel is 3.142 divided by 4. So I'm just taking it down. So we have external diameter of copper was given as 30 millimeter, which is 30 by 10 to the power of minus 3 all squared, minus the internal diameter was given as 24 millimeter, which is 24 by 10 to the power of minus 3 all squared. Okay, so I'm taking this off now. All right, so let's do all of this and obtain an area for steel. So area of steel is equal to, I'm going to be pointing everything at once, so do well to also point along to avoid calculation errors. Okay, so after evaluation, the area of steel gave us 2.5 by 10 to the power of minus 4 a meter squared. Okay, so this is area of steel, and not forgetting the area of copper itself gave us over here 4.9 by 10 to the power of minus 4. All right, so I'm going to be flipping over now. So we are putting these values into this equation here. Okay, for the stress of copper is simply equal to stress of steel multiplies area of steel all over area of copper. Now we know the area of steel, we also know the area of copper. We simply put into this equation. Okay, so keep this equation in mind. All right, so once more, the stress of copper equals stress of steel times area of steel all over area of copper, where area of steel was given as, we obtained it as 2.5 by 10 to the power of minus 4, and area of copper was obtained as 4.9 by 10 to the power of minus 4. So let's plug into this equation now. So this simply implies that the stress of copper is equal to stress of steel times area of steel 2.5 by 10 to the power of minus 4 all over area of copper 4.9 by 10 to the power of minus 4. So let's obtain this ratio. So this implies that stress of copper is equal to, let's obtain that division now, and that gives us 0.51 stress of steel. So this simply implies that the stress of copper is equal to 0.51 the stress of steel. Okay, so let's call this equation 2. Okay, so having found this now, it means we can go back to equation 1 in place of stress of copper, putting the value as this. So substitute into equation 1. So let's fall back to equation 1 and see what we have there. So in equation 1, we had 1 by 10 to the power of minus 11 sigma c plus 5 by 10 to the power of minus 11 sigma x, that's equal to 3.2 by 10 to the power of minus 5. So we can simply put that into this equation. So let me rewrite equation 1 over the other side of the book. Alright, so this is what we have from the perspective of equation 1, okay? So we are now substituting this value in place of sigma c into equation 1. So this becomes 1 by 10 to the power of minus 11 in place of sigma c. Sigma c is 0.51 sigma s, and you have this plus 5 by 10 to the power of minus 11 sigma s, and this is equal to 3.2 by 10 to the power of minus 4. So let's now expand this bracket. 0.51 multiplies 1 by 10 to the power of minus 11. So that gives us 5.1 by 10 to the power of minus 12. So we have 5.1 by 10 to the power of minus 12 sigma s, plus over here we have 5 by 10 to the power of minus 11 sigma s, and this is equal to 3.2 by 10 to the power of minus 4. So you observe that with this, we have been able to make this equation in terms of sigma s, so we can find the first stress. So let's add these two equations up. So adding these two up gives us 5.51 by 10 to the power of minus 11 sigma s, and that's equal to 3.2 by 10 to the power of minus 4. Okay, so from here we can make sigma s, solve it on the formula, simply dividing both sides by 5.51 by 10 to the power of minus 11. So this simply implies that sigma s is equal to 3.2 by 10 to the power of minus 4 divides 5.51 by 10 to the power of minus 11. Okay, and this will give us a value for the stress induced in the steel. That gives us 5.81 by 10 to the power of 6 newtons per meter squared. So this simply implies that the stress induced in the steel material is actually 5.81 mega newtons per meter squared, and that is the stress induced in the steel material. But not forgetting in equation 2, okay, let me just pull it out. This is equation 2. We obtain that stress induced in copper is 0.51 stress induced in steel. So that simply implies that, recall, stress in copper is 0.51 stress in steel. So this simply implies that the stress induced in the copper material is 0.51 times 5.81 mega newtons per meter squared. So this simply implies that the stress induced in the copper material is equal to, so let's obtain 0.51 multiplies 5.81, that gives us 2.96. That gives us 2.96 mega newtons per meter squared. Alright guys, so there you have it. Those are the stresses induced in the steel material and in the copper material. Alright guys, so that's it on thermal stress analysis. Once more, if you're new to the channel, do well to like our videos, comment nicely, and subscribe if you're new. I will see you in the next video. Thanks and cheers.